Good morning everyone and welcome back to our CNC Techniques channel. Today we start with a practical example regarding the use of Sinutrain and ShopTurn for various ISO programs. I remind you that I've already made videos both on the Wagner and with the help of the simulator, so I refer you to the old videos on our channel for the basics of programming. Now, the piece I want to create is this one. I didn't come up with a special piece. I simply took a piece that can also be found in some manuals that come with the machine, but it already starts to tackle the topic of roughing, grooves, and threading. So the first thing we need to do is enter the program manager, which is this little button here. Go into the parts folder, highlight it, and create. You see that with this submenu, we switch between the two soft key options on the right side of the machine, so everything related to program manipulation. We need to create a new piece, and since we have little imagination, we'll call it tree, even though it's not a tree, and we hit OK. As I already showed you, it automatically creates a directory, not a real program. After creating the directory, which in turn is a subdirectory of the parts folder, it tells me new program. So here we start talking about the program. We name it the same as the folder unless you want to change it. I can modify it however I want. Last time you worked in G-code in ShopTurn, I assume you want to work in ShopTurn again. If I want to work in G-code, I repeat. I need to press this soft key. Otherwise, we continue in ShopTurn. OK. The program opens. And right away, without going through the start, I'm asked for the origin I want to work with, and basically the dimensions of the raw piece. I find the only limit, let's say, of these conversational systems at least. Both the Fanuc and Siemens systems have the limitation that I couldn't figure out if it's possible to create a raw part that can be a polygon. For example, you see a centered parallel piped or tube, but it doesn't allow me to define a profile. If I'm starting from a preformed piece, I can't do it. So I either have to do roughing with a virtual tool using very aggressive parameters, which kind of tricks the machine, or I have to settle for standard shapes like cylinders, tubes, centered parallelepipes, or polygons. ZV, which is our reference point Z0, we leave at 0, then X is at 80. So that's the diameter of the raw piece. Z is the excess, metal on the first face, 2 meters. Z is the length of the piece, and ZB is the part of the piece that sticks out from the clamps. So we set it to minus 92. Release. Simple release expanded to everyone. I've already explained it in the introductory tutorial. In this case, we use a simple release because, as you can see, I will always need to release simply in Z and X. This is a junction where paths meet. Simple release is used to release in Z and X with 200 mm in both directions. Adjust later if needed. The tool change point is set with SCP as S1, the RPM limit. Positioning the mouse over a box gives an indicator. I leave 200 mm of release in both X and Z, meaning I will move away to release by 200 mm incrementally in both X and Z. I can modify this later if I see that I'm moving too far away, but for now, while I'm setting up the initial program, I can proceed without worry. The same goes for the tool change point with SCTM. Teach. The tool change point, meaning it learns it with. SCP, I set it as S1, which is basically the limit of RPM that the machine can reach at its maximum. Even if I'm working in the center, our machine will never exceed 3500 RPM. SC is the safety distance, and the direction of machining is consistent. Keep in mind that when you position the mouse over a box, it also gives you an indicator. Keep in mind that when you position the mouse over a box, it also gives you an indicator. So, as you can see, we're changing the tool in the Z-axis, and we've entered our nice little program. Now, it's time to face our workpiece. Let's go ahead and face it. Here we have options for drilling, turning, profile turning, milling, and also the possibility to change the soft key to straight or circle. This is useful for making movements that are separate from work cycles, like threading or roughing. In short, it's ISO programming but conversational. Perfect. Let's press straight or circle, and automatically the menu changes. The first thing you do is what you do when programming in ISO, which is to select the tool and cutting parameters. First the tool, and then tool selection. It automatically takes me to the tool page, where I've already preloaded tools in the machine that will correspond to my turret, and I'm going to create my facing operation. So I select the tool store, choose the tool, and remember that we can also add comments. Here, for example, we can write CNMG 80. By clicking OK, you can see that there's an additional comment here, but we carry it with us every time we use that particular tool. For the speed, we can set it to either RPM or meters per minute. Just click here to change the mode. Let's set it to 180 meters. And, of course, we're doing turning. Great. Now we need to approach the workpiece, so let's go straight. We said that the diameter of the piece is 80, so we set it to 82. For the Z-axis, we set it to 0.3, and we won't set an F value because this is just an approach, so we'll say it's rapid. Accept that, and now the machine moves close to the workpiece. So, straight to X, I'm going to face it, so -1 point. We set Z to 0.3, and we give it an F. No, we don't give it an F, because this is just an approach. So we set it to rapid, accept that, and now the machine moves close to the workpiece, so straight to X. I'm going to face it, so -1 point. Why 1.6? Because the insert radius is 0.8, as I already explained in the previous videos related to tool radius corrections. If I chamfer at x0, there will be a bevel left from the tool's radius that won't be removed all the way to the center of the piece. Here, I'm not going fast anymore because I'm performing a chamfer, but I'm setting a feed rate of 0.3. Then I accept, so I don't write anything in X, but I write Z1 in rapid, and accept. I've moved away in this straight direction, X82, and I need to specify again that it's a rapid move. I accept, and I've raised myself up, so I've done my chamfer and left a 0.3 excess material. Let's detach ourselves and always move away rapidly to X120, Z200, rapid, accept. We've completed the first chamfer. Do we want to see what we've done? Let's go to simulation. And here's what we've done. Do we want to see it in 3D? Let's press start and review what we've done. Look at this beautiful simulation. When I press start, the clamps begin to rotate, and I have an arrow indicating the direction of rotation. So, if by chance I've set the wrong rotation direction for my tool, the little arrow will change. Let's go check that out. So let's go to the Machine Program Manager. Wait a second. Now, let's take a moment to appreciate the precision and accuracy of the simulation. Notice how every detail is captured perfectly, ensuring that the final product will meet our exact specifications. This level of detail is crucial for achieving the desired outcome. Let's proceed with caution and ensure everything is set correctly before moving forward. Here it is. Tool parameters, tool list. You see here that we have it. Let's reverse the direction of rotation. Look here. We have the piece that is stationary, the piece that rotates in one direction, and the piece that rotates in the other. Okay. Let's go to inverted. The program manager might not know if it's been inverted, and if we do it maybe twice, it stays the same. So, machine parameters, tool view, inverted program manager, simulation. Look, I'm breaking the tool. The boss is going to get mad. Wait. Let's go back to machine. Parameters and change the direction of rotation. You see, graphically, if observed well, I mean, if you listen to the machine, this ShopTurn is really valid. Let's go back to our main program and start thinking about roughing our piece. Now, be careful here. I would pull Simon's ear a bit, because rough turning, I'm going to rough it. No, it's not like that. So let's stop the cycle. You need to switch when you have a profile. So when you have a drawing to execute in profile turning, you see that even here, roughing can confuse a user who doesn't know the ShopTurn well. So, profile turning. And first of all, new profile. New profile that needs a name. We can call it profile, because the profile we are going to create will be saved in the subfolder we are working in. So if we have 10 programs with 10 profile names, they will never get mixed up. Let's accept that. Now, we need to insert the starting point. I have faced it at 0.3, so I will start working from the E center of the piece, so X0, Z0. I will rest the tool here, and honestly, I wouldn't work exactly like this, but I'm kind of following the example given by Siemens. I would have faced it twice at Z0 and then rested here. And since I like to do things properly, interruption. I reject the changes. Okay. And I go back. I've reached Z0.3 at X82. Let's make a small adjustment to this program. That is, line, circle, line, Z0. Quickly. I accept. You see that the change has been made here in the middle, so I still have my release point. Line X minus 1.6. F0.3. I accept. Straight. Line Z1. Quickly, I accept. So I first faced at 0.3, let's say. I roughened it, and then I did a nice facing at Z0, so I won't have vibrations, and I'll have a nice surface. Now I move over here and go back to turning my new profile. Accept the profile, so I'm no longer starting from X0, Z0, because honestly, starting and finishing from the center of the piece will almost certainly lead to incorrect wear of our product, but I'm starting at X25, Z0. You see here, it asks me how I want to finish the next movement, chamfer, radius. If I set it to 0, it won't do anything, regardless of what I've written here in the automotive section. Lately, I'll show you this only once. It's always asked to put a small radius at the end of each movement. So radius 2, because the piece will look nicer. Now you see that I haven't written anything about the tool radius correction. Since I'm making a profile, when I do the finishing, the machine will correct the turning movement based on the tool radius indicated in the tool table. Accept. Perfect. I've entered my first point. So having entered my first point, I start moving upward. I have an M30X1 pi, so what do I do? Z0. You see here it asks me how I want to finish the next movement. Chamfer, radius. If I set it to 0, it won't do anything, regardless of what I've written here in the automotive section lately. I'll show you this only once. It's always asked to put a small radius at the end of each movement. So radius 2, because the piece will look nicer. Now you see that I haven't written anything about the tool radius correction. since I'm making a profile, when I do the finishing, the machine will correct the turning movement based on the tool radius indicated in the tool table, except, perfect, I've entered my first point. So having entered my first point, I start moving upwards. I have an M31.5. So what do? I'm moving upwards. Actually, let's go back. I'll show it to you again later. X30. Chamfer 1.5. Vertical move. Machine decides. Chamfer not made. Unknown destination. Left to 17. Z 17. Defaults 180 degrees. Chamfer 0. Sharp edge. To X40. Radius 2.5. Change to radius 2.5. Enter to register. No radius yet. Next move. X50. Z 30. Angled move. X50. It automatically takes me to 180 degrees because I didn't specify anything, and that's normal for the movement I requested. Chamfer 0, I don't put anything, so it will give me a sharp edge. Alright, I've arrived here. I'm moving to X40, so a vertical movement to X40. Radius 2.5, so I'm going to change the chamfer to a radius, and here I write 2.5. I always have to hit enter, otherwise it won't register, except you see that it hasn't set any radius because it has to wait for the next movement, which will be to X50, Z minus 30. So neither this one nor this one, but this one. That is, I'm automatically telling the machine that I will move at an angle. Perfect, so we said X50, Z minus 30. Minus 30 is here, I don't have any radius, so I accept. Stop. Minus 30. Minus 30 is here. I don't have any radius, so I accept. In automotive, a 0.2 radius is appreciated. Accept. Moving to Z44, radius 2.5, then raising to X60. It is always welcome, even if not required by the design. Accept. You see, we've gone here. Now I'm moving to Z44 with a final radius of 2.5. So, a horizontal movement to Z44, radius 2.5. Accept, and I'm raising to X60. I made a mistake, so I interrupt and go with the correct soft key to X60. Accept. Here I have 2 drains, 2 grooves, but I'm not going to program them, because that will be programming I'll do later. Now I'm moving to Z70, so a horizontal movement to Z70. You can also do the movement incrementally if you want, so in this case, I made a mistake, so I interrupt and go with the correct soft key to X60, except here I have 2 drains, 2 grooves, but I'm not going to program them because that will be programming I'll do later. Now I'm moving to Z70. So, a horizontal movement to Z70. You can also do the movement incrementally if you want. So in this case, you should have entered the difference between minus 44 and minus 70, but we work in absolute because it's more convenient. Perfect. We've arrived here. Now we raise to X66, anticipating a radius of 1. So, no, look, I closed the profile, I made a mistake. So I go back into the profile. You see it brings me back here, and I continue it. So, we raise, as we said, to X66. Radius 1 refers to the distance from the center of a circle to its edge. Except, we've arrived here. So now, we go to X75 always. Radius 1. Sorry. To Z minus 75. Radius. Let's set it to 1. Radius 1. Accept. And now we move to Z. To X. Sorry. 80. With the chamfer indicated here of 2 by 45. So chamfer 2. Accept. And because to make him do the chamfer. We can simply this time move incrementally by -5. Accept. Perfect. We've set our profile. At this point, we're going to accept it. But you, see, here, you haven't provided any instructions on how to work the profile you've just inserted. So now you need to do a roughing. I went a bit crazy because I created the profile the first time, went into turning and did roughing. No, that's not it. Stay in turning. Profile. Okay. It reads the profile you've created, and you tell it now. Rough it out for me. How? Rough it out for me, please. With the roughing tool, kindly rough it out. At a feed rate of approximately 3/10 per revolution, and rough it out at about 180 meters per minute. We can just do the roughing here. Simply. Just the finishing, which is not our case, or the roughing plus finishing, but that's not our case either. Right now we just want to rough it out. We want to do a longitudinal roughing and external roughing. You see, radial roughing can also be done this way. We want the machine to remove 5 mm on the radius with each pass leaving. 3/10 of excess material in X and just 1/10 of excess material in Z. We don't put it in, so D0 will attack and never detach. If instead we put a DI, every so often it will detach to break the chip. The description of the workpiece is a cylinder, and we already know that. As for excess material, we said we don't have any in Z because we programmed up to 80. If my raw material had been 90, I would have had to write the profile up to here, leaving 10 millimeters, actually 5, because we're talking about a radius. We haven't programmed any undercuts. These would be the undercuts, so we won't have any. You see, we'll program them later. It's always better to program undercuts at a later stage. As for boundaries, we don't set any limits, which could be clamps or special fixtures. We've done a good roughing, and now I want to finish it. So I'll add a second roughing, change the tool, select the tool, and set it to 35 degrees for finishing with a radius of 0.4. Okay. So I've changed the tool and adjusted the parameters, roughing at 1.5/10 per revolution. I'm going a bit faster with the feed, but be careful. I need to modify the cycle, so it's just finishing. An external finish, longitudinal, in the direction of the spindle of the self-centering chuck, with no excess material, no undercuts, and no boundaries. Let's accept and simulate. So simulation impossible, invalid tool, name. Let's take a look. Okay. Let's go to the little arrow. I select the tool because I've changed its name. So I need to modify it. Let's accept and simulate. You see. It's a German tool, so it requires certain adjustments, the correct sense of rotation. We've done the chamfering, and now the roughing tool is coming in, and you can see that it's roughing out its nice profile. We can move on, and now the finishing tool is coming in. Perfect, we've done everything we wanted to do so far. Now we need to think about the discharge, so let's go back to our program. We go to the end and select turning discharge. You see that we don't have just one discharge option available, but a series of possible discharges depending on the shape. This one is recessed. This is the DIN discharge. We have a threading discharge to perform. So the first thing we need to do in this operation is to insert the tool. We can easily use the finishing tool at 35 degrees. That's perfectly fine. 1 millimeter per revolution. And we'll set a cutting speed of 150 meters per minute. All right. What type of discharge is it? Longitudinal is just fine. We need to do a finishing, or rather, let's do a roughing plus finishing so we can work properly. We need to input our data, so we have an x0, which is this, meaning the diameter of our thread is 30 millimeters, and a z0, which is where we need to reach, as indicated. So we will go to -17. An x1, which is the depth, we can set it to absolute, but in this case, let's set it to incremental because we're going to input the depth of our discharge, 1.15. Then it will be adjusted as needed. A Z1, which we will also set to incremental, is the length of our discharge. .5, after which we have the R1 and the R2, which are these two radii. So R1, we will put 0.8 and the R2 0.8. So 0.8, 0.8. You see that these values, when the radii were too big, let's take an example, 4 and 4. They marked them as incorrect because I can't set 2 radii to 4 if I want to achieve a thickness of 4.5 meters. So it has to be 0.8. If ShopTurn finds any inconsistencies, it will notify you. Alpha is this angle, and I'd say it's pretty clear. Vix is how much we want to raise before we move away. We can set it to 1 millimeter, just a little bit, or we can set the diameter to 40 to go over it all. It's a bit up to personal preference regarding the depth of cut, so 0.8 is just fine. Now, I need to set Vx to incremental. If I set it this low, that's why it was giving me an error. If I don't set it to incremental, it goes to diameter 2. Instead, I set it to absolute incremental. And then, Ux and Acuz, any offsets I can also set to 0. Oh no, I need to set them. Sorry, since I chose this option, I set them to 0.1 to 0.1, so that in the roughing and finishing option, it will rough while leaving this offset, and then finish by removing it. So in the end, we will have the actual measurements. Okay, I think we're good. I see I set 4 and 5 out of habit, but the drawing shows 4. Set it 4. Let's accept and simulate. Let's expect our finishing is done. And here's our rough unloading. Look how beautiful it is. The ShopTurn graphics are stunning. And now let's get back to the program. All right. It's time to think about the thread. So let's select the turning thread soft key this time, which means the profile of the rest doesn't matter anymore. like it did for the unloading. I might not have mentioned it before, but we switched from turning for unloading because it's a standardized option. So let's select a threading tool. Here we go. Perfect. Now let's input our data. The pitch, of course, corresponds to M30 for 1.5, and the feed is 1.5 millimeters per revolution. So G is the variation of the pitch per revolution, and it doesn't change. I want to thread at a constant pitch of 1.5. Normally, threading is done at fixed speeds, so we can set it to 500 RPM. The thread is roughed out and finished in one linear pass, so we descend in a nearly constant manner. We're making an external thread, and remember that the blue point corresponds to what you're about to input, 30Z0. C1. Z1 is the depth, the length of the thread, so minus 16 mm. LV is the safety distance from which we want to start. I usually set it to 3, which is twice the pitch of 1.5. LR, on the other hand, is the distance at which the machine will tend to disengage. 2 mm should be fine. H1 is 0.92, and you can see that it automatically adjusts itself. Anyway, it's the height of the thread at P, which is the degrees, and is perfectly fine at 1. The depth, I'll refer to the depth increment table. So 0.3 is really a lot, 0.15 is the excess material that we'll leave for finishing, and VR is when we're going to pull away during the return phase. 1 min medium, 2 min. It doesn't change much because doing it quickly is really fast. Perfect. We accept our threading and simulate our program. It would be nice sometimes, since the file is very detailed, to start only from what interests us, but normally we'll simulate only at the end. Otherwise, our boss will come and pull our ears. Let's check the threading to see if we did everything right as a Fanuc lover. I'm a bit amazed because obviously a graphic like this is something Fanuc can only dream of. All right, what do we have left to do? We have to make the 2 grooves, so we go to groove turning. Here it is. Let's select the tool right away. You see, once you understand the concept, they're all the same. We have a tool for external grooves, thickness 3, and the tip radius is 2. And VR, which stands for virtual reality, is a fascinating technology that allows us to create immersive environments. This technology is used in various fields such as gaming, education, and training, providing users with a realistic experience that can enhance learning and entertainment. In this context, VR is when we're going to pull away. During the return phase, 1 millimeter, 2 meter, it doesn't change much because doing it quickly is really fast. This rapid movement is crucial in ensuring efficiency and precision in our operations, as it minimizes downtime and maximizes productivity, allowing us to achieve our goals more effectively. Perfect. We accept our threading and simulate our program. The simulation process is vital as it helps us visualize the entire operation before actual implementation, allowing us to identify potential issues and make necessary adjustments. This step is essential in preventing costly errors and ensuring that the final product meets the required standards. It would be nice sometimes, since the file is very detailed, to start only from what interests us, but normally we'll simulate only at the end, otherwise our boss will come and pull our ears. This humorous expression highlights the importance of following protocol and ensuring that all steps are completed in the correct order, as skipping steps can lead to mistakes and inefficiencies. Let's check the threading to see if we did everything right. As a Fanuc lover, I'm a bit amazed because obviously a graphic like this is something Fanuc can only dream of. Fanuc, known for its robust CNC systems, often lacks the advanced graphical capabilities seen here, which can be a limitation in certain applications where visual representation is crucial. All right, what do we have left to do? We have to make the 2 grooves, so we go to groove turning. Groove turning is a critical process in machining, allowing us to create precise grooves on the workpiece. This process involves careful planning and execution to ensure that the grooves meet the required specifications, which is essential for maintaining quality standards. Here it is. Let's select the tool right away. You see, once you understand the concept, they're all the same. We have a tool for external grooves, thickness 3, and the tip radius is 2. This tool is specifically designed to handle the demands of groove turning, ensuring accuracy and consistency in the final product, which is essential for maintaining quality standards and meeting customer expectations. The radius of the tip is 2. Let's select a feed rate of 1/10 per revolution for a groove. That's more than enough. 120 meters. Today, I haven't worried too much about the material we're working with and the parameters. So, when machining grooves, we rough them out and finish them only in special cases. We change the tool when we have a specific groove bottom, position. Do you see how the groove is? It's on the outside, it's frontal, it's internal, it's pulled in. What is the 0 point of the groove? Reference point, right angle. What type of groove do we have? Do we have a square groove? Do we have a groove on an inclined plane? Or we have, as it interests us, a groove with radii at the bottom and chamfers. So this is misleading because you say, no, I don't have a trapezoidal groove. No, it's true that you don't have a trapezoidal groove, but you do have some chamfers here at the entrance and groove bottom radii R1. Okay? If you use this, you can't put the radii at the bottom of the groove. So use this, and our angle will simply be a 0 angle. So, let's start collaring them. Look at the X. Here, it's 60 of the outer diameter, the base point of Z0, which is this, you see, 55 thickness, 6. So, Z minus 49. B1, width of the throat 6. T1, the depth is 3. Here we go. As for the alpha angles, I don't care about them, so I leave them at 0 for alpha 1 and alpha 2 because my groove is straight. FS1 chamfers, 0.5, FS1, 0.5. Be careful that these are not the two internal chamfers first, but they follow the drawing, and it's well indicated at FS2. FS3-1. Be careful because there's a mistake in everything I'm doing, but I'll explain it to you now. 0.5. You see that here some radii are indicated, but actually FS2 and FS3 are radii, while FS1 and FS4 are chamfers. So, for FS1, you see, I can do it. I can transform it with a double click into a radius, you see. RFS, chamfer. So now I will have FS1, chamfer, R2 flat, R3 radius, F4, chamfer of 0 because I want to work planted. If I want to break the chip, I put a D1. And every millimeter the machine will stop for chip breaking. UX during the finishing phase. And in the roughing phase of 2/10 of excess material, that's fine. How many grooves do I want to make? I want to make 2 grooves, so by making 2, a second table automatically appears. How far from corner to corner? From corner to corner it's 55 to 65, which is 10 min. Since the machine can make a groove to the right or left of the first, the sign is important. Let's accept and simulate. Simulation impossible, invalid tool position. Okay, let's see why. I must not have done it. Okay, tool selection perfect. It also adjusts the speeds that it didn't take into account. And I insert finishing plus roughing. Accept and simulate. Simulation, which is always a pleasure for the eyes. I don't remember if I told you this before. At my age, memory is what it is. Here you also have an estimate of what the final work time could be. It's an estimate, so take it with a grain of salt, but it's definitely an interesting indication. Now it's getting ready to do the threading, and then the last operation that interests us, which is the grooves. Here, even the ShopTurn programs the movements in a less profitable way compared to ISO programming. However, if you're making single pieces, it's definitely a fantastic approach, and even for small batches. I mean, you see, it does the roughing, the finishing, and then moves to the second groove. The movements you've seen that seem a bit strange are due to the safety distances. And here we have a finished piece. The machine tells us, look, it would take you about 4 minutes, and 42, and you can watch it. See. Perfect. Well, once again, we've reached the end of our work. I hope it was of interest to you. We'll continue with the shop tour and other examples of processing in the coming days, and then maybe we'll also take a look at some ISO programming with the Sims. I thank all of you for your attention, and if you liked the video, as always, give it a like, and if you can, share it with everyone who shares our passion. Thank you all, and have a great day.